Yeah. All right. Continue this. Yeah. Thank you very much for the invitation. And yeah, I've been lurking around in this seminar series for a while, and it's a really good seminar series. So I'm happy to finally be able to contribute. So yeah, as Nadir said, I'm going to be talking about MMC for Multilevel Monte Carlo for computing probabilities. Let me just start by acknowledging my collaborators. So this is joint work with Jonathan Spence from Harvard University and Aretha Tegentroop from University of Edinburgh. And as you will see throughout this talk, it actually started as a continuation of a work with Mike on nested expectation, and evolved into what it is today. But I've had very valuable input from Mike as well in the development of the project. And I also want to acknowledge that Jonathan has been the main contributor or main workforce for this project. So all the analysis and the numerical experiments are mostly done by him, and he probably will be able to answer questions better than I do. Okay, so let me talk first about the problem. So the problem is fairly generic, fairly useful, which is computing probabilities of this form. So we're computing probability that a random variable x is in some d-dimensional domain omega, which I'll write as an expectation of an indicator function. So x is my random variable. So there are two main reasons why this is a challenging problem. The first one, which I will not be dealing with in this talk, is that the event is rare. And that is to say that the omega is small compared to RD, for example, or the probability concentration in omega is small. So there are many methods to deal with this. There is the methods, importance sampling or particle filter methods. There are many good methods to deal with that problem. The other challenge that I'll be dealing with in this talk is the complexity of sampling X. So X might require some effort to sample. So perhaps this is best represented by an example. So here I'm actually introducing three problems that our methods will deal with, and there are three representative examples of underlying concepts. So the first one is financial risk assessment, where X is defined as an expectation with respect, an expectation of a random variable Y with respect to, or conditioned on a risk scenario R minus some loss. And then the interest there is to compute the probability that this expected loss over all risk scenarios is large compared to the loss. So X here is, again, the expected value minus the loss. So this is an important, you can think of the expected value of Y as just the expected loss for, as I said, a risk scenario. Another important example is digital options, where X is S of T. S is the an asset price that follows an SDE or satisfies an SDE solution minus a strike price. And X, when X is positive, then the digital option is exercised. Otherwise, it's not. And then the expected value of, or the probability of exercising that digital option is what's of interest here. So the expected value of the indicator of this ST greater than K. And finally, the third example is the component failure, where the X random variable is just defined as a functional of a Y, another random variable. But in this particular case, for example, G depends on a solution of a PDE, and the Y, for example, are the random coefficients, or they control the random domain or the random initial conditions. And you can think of G of Y as the proportion of components that have failed in a system. That system being modeled by a PDE. So all these three examples are of interest. And what's particular about them is that all of them require some approximation. So in the first case, this inner expectation, this expectation for a given risk scenario, we might not be able to compute it exactly, and then I have to approximate it using a Monte Carlo estimator, for example. By the way, I have to interject here and say, if anybody has any questions, please feel free to interrupt. I don't have that many slides, and hopefully I should be able to adapt. Okay, so that's the first one, where I have to approximate the expectation with a Monte Carlo estimator. The other one is I have an SDE solution, where the SDE solution now has to be approximated, for example, I cannot sample the SDE solution exactly, and I have to approximate it using an Euler-Mariama or Milstein scheme with a step size h. And finally, in this example, G, for example, depends on the PDE. I cannot solve the PDE exactly, so I have to approximate it with some approximation method like Runge-Kutta with a step size, with a grid size h. So all of these have in common is that there's an approximation parameter h, which I'm sure is not a surprise to the audience in this seminar, where that the complexity of each one of these three increases with the approximation parameter. So if n increases or h decreases, but also the complexity increases, but also the accuracy increases. So this balance is what's important. Finding this balance is important. So just to get ourselves familiar with the notation and for comparison, let's just talk about the Monte Carlo complexity. So here I'm assuming that my random variable x, I can approximate it with an xl, L being a natural number, and L is the XL is the approximation. As L increases, I have better and better approximations. And here I assume that the work grows like 2 to the power gamma L, while the bias decreases like 2 to the power minus alpha L. The 2 is inconsequential. It's just for nice notation. So in this case, again, X here can represent anything it wants. It can depend on an nested expectation. It can depend on an SDE and a PDE. It doesn't matter. And in this case, I have the expectation of the indicator. I can estimate it, especially when X has high dimensionality. The best method to estimate it is using Monte Carlo. And I can take M samples and evaluate the indicator function for these M samples, and then get the average. And fairly straightforward complexity analysis tells you that M has to be epsilon power minus 2 for an error tolerance in the estimate of the probability of error epsilon. It has to be the number of samples in this Monte Carlo estimator has to be epsilon power minus 2, while the level of approximation, which I should have talked about here, that I had to take a high level of approximation of X. That level of approximation should be taken like log epsilon to the over alpha, such that the bias is of order epsilon, and then the complexity is of this order. As a representative example, assume alpha is equal to gamma equal to 1, that's epsilon power minus 3. And that's clearly not the best we could do. The best we could do actually is with multi-level Monte Carlo, where, well, best in some sense, where the expected value, now I'm going to be focusing on the expected value of some function f of x. So I recognize that to this audience, this is a very generic, it's a very known method, but I'm going to just go slowly through the presentation in this particular section, just because there's a small difference in the presentation in how I'm presenting things. And I'll emphasize that. So here I'm having the expected value of f of x. F of x in our case is an indicator function, but things just generic f. And again, we're assuming that I can approximate x with xl, where L is a natural number. And here I have the same assumptions on x, not on f of x. So I have these assumptions on x, L, and on x and xl, the approximation. So the work is 2 to the power gamma L. The bias is 2 to the power minus alpha L. And I have this extra assumption for multi-level Monte Carlo, where the variance is 2 to the power minus beta L. So that's the variance of the two approximations at different levels, L and L minus 1, decreasing with the rate beta. And this gives you the trifecta of parameters, alpha, beta, gamma, that are important in multi-level Monte Carlo to tell you what the complexity is based on the relationship between beta and gamma. Well, that depends. This is the multi-level Monte Carlo estimator. For those who don't know, it's just based on the expected value of x being written as an infinite sum, infinite telescoping sum, and then truncating that sum to a certain level L to get a biased estimator, and then estimating each expectation with Monte Carlo estimation. So I said that depending on the beta and gamma, that's how I know the complexity, but that depends really on the functional that I'm trying to compute f. So if f is differentiable, then I can fairly quickly prove that the function f of xl and versus f of x inherit the same rates of alpha, beta, and gamma. So the work is again 2 to the power gamma L. So these are the assumptions on XL, on the work, bias, and variance, and they exactly carry over to f of XL. So the work of f of XL is 2 to the power gamma L. The bias is again decreases at the rate of alpha, 2 to the power minus alpha L, and the variance is 2 to the power minus beta L. So that's great because then I can tell you what the complexity of multi-level Monte Carlo is based on just computing the total work of it with to be in the best case scenario epsilon power minus 2 when beta is greater than gamma. So that's for the estimation, for the multi-level Monte Carlo estimation of expected value of f of x when f is smooth. So it depends on the relationship between beta and gamma. If beta is greater than gamma, I get epsilon power minus 2. If beta is equal to gamma, I lose a log factor. And if beta is less than gamma, I get this factor here, which is an improvement over Monte Carlo, but not as good as this one. And the proof is fairly well-known, I assume, in this audience, but it's just based on selecting a good or optimal selection of number of levels in the multi-level Monte Carlo estimator and the number of samples per level. Good. So that's the smooth F. That's the nice case. But that's not the case we are interested in. We're interested in probabilities, which are expectations of indicators, which are discontinuous. So the functional is discontinuous. And for this, we need a different kind of analysis, different or additional assumptions. So let me introduce those assumptions. And those will be the last set of assumptions that I'll be introducing in this talk. So the second set of assumptions is that sigma, I'm assuming that I have some sigma L greater than 0. This can be a random parameter, but think sigma L is equal to 1 for the purpose, for most purposes. We will see an example where it's not 1, but for most purposes, just think of sigma L equal to 1. Then define this parameter delta L, which is the distance between XL and the boundary of sigma. So this tells you how far my approximation is from the boundary. It effectively tells you how far my approximation is from changing value, because at the boundary is when the indicator function changes value. Okay, so that's the key quantity here. I'm dividing it by sigma L that I've chosen, but again, think sigma L equal 1. And then I make two key assumptions. The first one is on the probability of delta L, and that is it's linear when x is small. So the probability is linear. And the second one is that the error of XL minus X has finite Q moments. Okay. Here I'm allowing a division by sigma L, which I chose, but again, think 1 for now. And let's talk about this assumption here. When Q is equal to 2, that's just saying the second moment of the error is 2 to the power minus beta L. So that's exactly what my assumption on the variance was for multi-level Monte Carlo. I'm here requiring a bit more. I'm requiring more than 2 to get a higher moments of the error, and the convergence rate is not affected as long as it's properly normalized. Okay, so that's the other assumption on the other key assumption. So these are the two assumptions that I'll be working on. And using those, actually, I can prove that the variance of this function, this indicator function with respect to x versus the indicator function with respect to XL, the variance of this difference converges like this factor here. So before I had that x and XL, the variance of the difference between x and XL converges like 2 to the power minus L beta. And here I'm losing two things. I have a factor here, Q divided by Q plus 1 times half. Okay, so I have this additional factor. And let me just quickly go through the proof, just because it illustrates the key ideas here. So here I have the variance of the difference that I'm looking at. I bound this variance by the second moment, and then I relate the difference of the indicator functions to the distance between x and XL. So this difference is either, since I'm taking the square, it's either 0 or 1. It's 1 when the x and XL are on opposite sides of the discontinuities of the indicator function, which happen to be on the boundary of omega. So when x and XL are separated by a distance more than the distance between XL and omega, and the boundary of omega, that's when I know that x and XL are straddling the discontinuity, or most likely are straddling the discontinuity. And then I have an indicator 1. So that's how I bound the difference between the indicator to the distance, to a function of the distance between x and XL. And then by dividing both sides by sigma L and by 2 to the power minus beta L, divided by 2, I get on the left ZL, which I have here. and on the right, a factor of delta L, which I had defined before. And then I separate this probability or this expectation into two parts. The first part when delta L is small, and the second part when delta L is large. And small and large are depending on this parameter here with P, or wiggly P. So this, I'm separating these two into these two quantities. When delta L is small, I don't care about the error at all, represented here by ZL. I only care about the fact that delta L is small. And I bound that by just that probability, that delta L is small. When delta L is large, I don't care how large it is, as long as it's larger than my constant. And that's how I bound this probability. So now I'm separating between two, I split this original expectation of the error squared into two parts. The first part when delta L is small, and again, delta L is the distance to the boundary of omega divided by sigma. So either delta L is small or the error is sufficiently large. If delta L is small, I'm using the first assumption that the probability on delta L is linear. And if the error is large, sufficiently large, I'm using Markov inequality and the fact that I have Q finite moments of this ZL based on the second assumption. And then by choosing this rho correctly, or this P correctly, I get the rate that I'm claiming here. So by choosing rho, P so that these two terms are equal to each other, I get in order, I get the claim that I'm having here, which is that the variance of the difference of these indicator functions, it's 2 to the power minus this factor, Q divided by Q plus 1, which depends on the moments, times L beta divided by 2. Okay, so I'm losing a factor of 2 here. What this means is that the Monte Carlo approximation or the Monte Carlo complexity now does not depend of this when estimating this expected value of the indicator, no longer depends on beta and gamma. It depends on beta and 2Q divided by Q plus 1 gamma. So beta not only has to be greater than gamma, it has to be greater than 2Q divided by Q plus 1 times gamma. And that's a stricter condition to get to the optimal complexity epsilon power minus 2. So for example, in the nested expectation, when X is some expectation depending on Y and R, that should be R, or when X is an SD example, then alpha is equal to beta equal 1, equal to gamma. And then even in the best case scenario, when I have infinite moments, so Q going to infinity, the Monte Carlo complexity is epsilon power minus 3. The multi-level Monte Carlo complexity is epsilon power minus 2 log epsilon squared when F is smooth. So this is because alpha is equal to beta is equal to gamma, but it's epsilon power minus 5 over 2 when F is continuous. And that's because beta is equal to 1, which if you take here Q going to infinity, I'm in this region here. So beta is less than 2 gamma, because beta is 1 and gamma is 1. I'm in this region, so I get back this complexity here, which happens to be 5 over 2, if you substitute. Okay, so the key idea that I'll be presenting here is based on adaptivity. So here I have my a simple example where I'm looking at the indicator function of a random variable X, the ith sample of the random variable X greater than 0, which I approximate by the indicator function of the L approximation of that random variable, again, greater than 0. And here I have the indicator function in gray in the back. And here I have my exact sample, X1, and I have the approximation here, and which lies somewhere in this, I don't know exactly where it is. It's somewhere in here, but I know that the difference between X1 and XL1 is of this order, sigma L times 2 to the power minus beta L over 2. But the key point here is that the indicator function here is exactly 0 because that's on the negative side. So this is the indicator function. So it's 0. And in my approximation, if it lied anywhere here, no matter how big the error is, as long as it lies on this side, it's 0. So the indicator function of that approximation. So I'm not making any errors. The problem only happens when the sample itself, so this is for a different sample and a different approximation, and the sample itself is close to this continuity, or the width here is close to this, the width of this probability density function crosses into the discontinuity. And then I have a significant probability of lying on the wrong side of this continuity, such that the real value of the indicator function is 0, but the approximation when I lie somewhere here and the indicator function there is 1, and then I'm making an error of order 1. That's what contributes mostly to my variance. And so the key idea here is that even though the L approximation level here was fine for this sample, it was not okay for this sample, X2. So what I will be doing is I'll refine this sample by an eta L. So instead of looking at just XL, I'm looking at XL plus eta L. I'm refining that sample, making sure that it lies within even closer to the real sample X2. And by doing that, I'm making sure that I'm on the right side of the discontinuity. Good. So that's the basic idea. And now I feel like, now that I've introduced all these concepts, it's good time to talk about previous research. So one of the first papers discussing this came by Mike, Haim, and Mao, Giles, Haim, and Mao, where they analyzed the recently introduced multilevel Monte Carlo for SDEs with non-global Lipschitz payoff. In particular, for example, for the digital option that I showed you before. And in fact, the analysis that I just showed on the variance of the difference of indicators is exactly what was presented here for the SDEs. It's just taking it a little bit and looking at it in a more general setting. But it's exactly the same analysis that was in this paper. Another paper that is of note is by Mike Nagapetian and Ritter, where they look at the multi-level Monte Carlo in the general setting that we have here, that I'm presenting here, but they use a different approach to get around the problem of this discontinuity, or this lack of, this reduction in the variance convergence rate. In particular, they smooth out the discontinuity. And doing that actually achieves similar results to what we're talking about here, but they assume different assumptions, or they have different assumptions, mainly on the differentiability of the PDF. And also they require some further analysis. The work they require further analysis for the effect of the smoothing parameter on the bias and the variance. This actually work does include that analysis in particular in some cases, but you might have to do that for your case. I mean, it will have to be checked on in a particular application. And again, the differentiability of the PDF here is different from the assumptions that I showed you before about on the moments. Another research that is more related to adaptivity is by Elverson, Hellman, and Malmquist. So this here, actually, they look also on multi-level Monte Carlo for computing probabilities, exactly what I'm talking about. And they also use adaptivity in the sense that they have samples and they selectively refine the samples. The refinement is slightly different. So here I'm phrasing it in terms of just Monte Carlo levels or approximation levels. There they phrase it based on just relaxing the condition or the indicator function. So accepting more and more samples, but it's exactly the same. It's in the same spirit, in the same idea. The restriction there is that they assume almost sure convergence of the samples. So this only applies to the third example that I showed you on the problems where I have an underlying PDE and with random coefficients, and I have almost sure convergence for all values of that random variable. Another relevant, very important work is by Brody, Du, and Walmy, where they actually introduced the idea of adaptive sampling for nested expectation. And that's actually was the basis for my work with Mike, where we looked at multi-level Monte Carlo for nested expectation with adaptivity, exactly what I talked about here. And that actually was the motivation for the generalization that I'm presenting today. There, we applied adaptive sampling for multi-level Monte Carlo with nested expectations. It requires slightly stronger conditions on the random variables than what I presented, which I'll explain in more detail in a bit, but also has different results, slightly better results than what we have. So there is it's not a one-to-one comparison here. There are advantages to both analyses. Okay. So now that I discussed all this, let me talk just what is the algorithm that I'll be focusing on. So the algorithm, again, refines XL to XL plus eta L. So that's how much I'm refining each sample of XL. And eta L depends on the value XL plus eta L itself. So eta L is defined as the first integer between 0 and L. So that's how much I'm refining. I'm only refining up to level L. I'm not refining more than that. So I'm not more, if I have a certain refinement XL, I'm not refining more than 2L. So eta L is the first integer that satisfies this inequality. So this inequality depends on delta. In particular, as delta goes to 0, eta L goes to infinity, but of course, I'm only checking up to L. And also it depends on L. And I hasten to remind you that delta L itself depends on XL plus eta L. So it's the distance between XL plus eta L to the boundary of omega, and also divided by this parameter sigma that I have free choice in. So this is the picture that you should have in mind. When delta L is large, I'm not doing any refinement. Eta L is 0. I'm just, the condition here is satisfied for delta L with eta L equals 0, and then I'm not refining any further. When eta L is small, here in this red region, then I'm doing the maximum number of refinements. So I'm refining L times. And in between, I'm just interpolating between 0 and L. Obviously, the eta L is discrete. That should be a stair function, but just for easy representation, just think of it continuously. So this is the picture when L is equals 3 and for a certain value of R. If L increases, then the region in which I'm refining decreases. So before L is 3, now L is 4. The region in which I'm refining decreases, and the maximum refinement obviously increases because it's 2 times L. And finally, R, as I said, controls this parameter R, which I assume is greater than 1, controls the interpolation between L and 0. So if L is close to 2, I have this kind of interpolation. As L decreases, I increase the refinement region of the over delta. And if R is close to 1, then I have a significantly larger refinement region with respect to delta. Okay, so with this, now I'm just going to present the theory, the theorem of the complexity or the variance and the work. So if I use this adaptivity theorem, we can prove that there exists some value of R, some maximum value of R, such that if R is between 1 and this maximum value, then the work is 2 to the power gamma L. So the expected work of this adaptive indicator function, functional of XL plus eta L. The work is still 2 to the power gamma L, so I don't have significantly more work than just if I don't refine at all, while the variance is this. So it again has this factor Q divided by Q plus 1, but now instead of dividing by 2, I'm dividing by this parameter zeta. Okay, so what is it? What is this zeta? Well, if beta is sufficiently large, so it's larger than Q plus 1 divided by Q times gamma, then zeta is 1. If beta is smaller, then zeta is 2 minus this positive factor here. So if beta is smaller than this, then I have an improvement over 2. Remember, when I didn't have any adaptivity, I had here 2. So I was halving my variance convergence rate. So when I didn't have any adaptivity, I had 2 here. Now I have slight improvement over it, or what's significant depending on how close I am to Q, how close beta is to Q plus 1 divided by Q times gamma. Okay, so that's my zeta parameter. So let me talk a little bit about the proof of the work and the variance, and then I'll talk about whether that results in the complexity of multi-level Monte Carlo. So for the work here, I'm plotting now delta versus the work versus of that delta L plus eta L. So this is exactly the same plot as before, except that I'm plotting, instead of eta L, I'm plotting the work of XL plus eta L. So it's 2 to the power L plus eta L. So when when the delta is large, I don't refine at all, and the work is 2 to the power gamma L. When delta is small, I refine L times, and the work is 2 to the power 2 gamma L. And so if I want to compute the expected work, I have to integrate this curve over the probability density function of delta. And so when I'm here in this region, I'm doing 2 to the power gamma L work. So that's what I'm claiming. When I'm in this region, I'm doing 2 to the power 2 gamma L work, but I'm only doing it for 2 to the power minus gamma L of the samples. So if you integrate this square here, this just 2 to the power minus gamma L times 2 to the power 2 gamma L, and the integral is 2 gamma L. And then there's this mid region, which happens to integrate to 2 gamma L, or to a constant times 2 to the power gamma L, as long as R is less than 1. And that's what this small calculation shows. I'm not going to go through the calculations. The only point I want to make is that one of the key ideas here is to relate eta L to delta L through this condition. So when eta L is equal to K, if I condition eta L being on some K integer, that tells me what delta L is in terms of inequality. It tells me what's the minimum value of delta L plus K, because it satisfied the condition that I talked about before, this condition here. So if I put here K, that gives me a condition on delta L plus K. And it also tells me about all the previous deltas for delta L plus M, for M equal 0 up to K minus 1. Essentially, it tells me that it did not satisfy those conditions because I'm doing this iteratively. And then using this condition, or using this equivalence between eta L equal K and the conditions on delta, I can estimate the work just in the usual way. And actually, this is very similar to, if you've attended my talk on nested expectation, this is very similar to the proofs there. The variance is a bit more complicated, but the basic idea is similar to what we talked about, and mainly that when delta L is large in this region, I'm not doing any refinement, and I can use essentially the Markov inequality and assume, using the fact that I have bounded moments, I can bound the error here. When delta L is when delta is small in this region, then I refine maximally, but using that actually because we know that we lose beta over, we lose half the rate, so we get beta over 2, but it's beta over 2 times 2L, because here I'm refining L, so I'm using not XL, but X2L, and I'm getting half the convergence rate, so it's 2L divided times beta divided by 2, so that's just L times beta. There's also, of course, the factor of Q divided by Q plus 1, but that just carries over. And then the mid-region has to be treated especially carefully, but it turns out to work out if one is careful. And it's exactly the same ideas here. But this is the ultimate result, and that is the complexity of multi-level Monte Carlo. In this case, is epsilon power minus 2 when beta is greater than Q plus 1 divided by Q times gamma, without this divided by 2 that I had before, without this 2, sorry, that I had before. So I don't have a 2 factor here that I had before. I only need beta to be greater than Q plus 1 divided by Q times gamma to get this epsilon power minus 2, or equal to get the log factor. So if I apply this to the previous example where alpha is equal to beta equal to gamma equal to 1, then, and I take the simplest case that Q goes to infinity, then the complexity of multi-level Monte Carlo is actually epsilon power minus 2 like epsilon squared, even with the adaptive sampling, even when I use the even with the discontinuous f. So the complexity of this functional of XL has the same complexity as a multi-level Monte Carlo applied to that function, applied to that XL. The functional doesn't hurt me, the discontinuous function. Okay, so let me give 2 numerical examples. The first is on nested expectation, and this is actually, if you've attended my talk on nested expectation, adaptive sampling with nested expectation, this is exactly the same example where I have a particular Y random variable. Again, this should be R. Particular Y random variable based on the risk scenario Z. And I have that I'm approximating the expected value with a Monte Carlo approximation with an NL samples, where NL is equal to the power L. So I'm just doubling the number of samples every time I refine in the inner expectation. This example is motivated from some loss incurred by an asset following Brownian motion, but it doesn't matter. It's just, think of it just as an expectation. So I'm taking an indicative function of an expectation. And this is where it's different from the previous work. And that is, well, first, this word is similar, that when I'm estimating this difference, so this difference is just the, I should emphasize this notation. FL is just the indicative function of not XL, but XL plus eta L. So FL is the indicative function applied to the adapted X, and delta L is the difference between the two. And so when I sample delta L, I use the same sample, the same risk scenario Z or R for both XL plus eta L and the coarser one XL minus 1, eta L minus 1. So both of these have the same, I'm using the same risk scenario, and this ensures the variance convergence. The second point is that we can reuse the samples when we refine. So we again start with XL and then we refine XL plus 1, XL plus 2, XL plus 3, all the way to XL plus L, depending on eta, until each time checking if my eta L satisfies the condition. And I can reuse the samples between each refinement, or I cannot, it doesn't matter. The theory does not assume independence in these iterations of the adaptive algorithm. However, the last step of the adaptive algorithm, when I do accept an eta L, must use the same XL plus eta L for the estimate. And this is crucially important. That's because the adaptive algorithm depends on the sample, and that sample should be used for the estimate of the indicator function. And that's different from the previous work on nested expectation, where we used independent samples, because essentially the value here converges almost surely to an expectation by the strong law of large numbers. So I don't need to use the same samples, but here I do need to use them for the theory to work. And sigma L in this case, sigma L would be not 1. Actually, if I choose it to be the sample standard deviation, then in this case, I don't need any conditions on X or the risk scenario, Z or R. I don't need any conditions on the moments, because what I will have is a self-normalizing sum, and the self-normalizing sum has finite Q moments. And that's a relaxation on the assumption, the assumptions from the previous work on nested expectation at the expense of this Q divided by Q plus 1 factor. But again, since this Q can go to infinity for the self-normalizing sum in this case, I can take this one to be as large as I want it to. So numerically, this is what it looks like. I have here, I'm plotting the work versus the level for the case when I use deterministic number of samples on every level. So NL is equal to 2L in the green, or I'm using the square of that at every level deterministically. So I'm not adapting anything. And here you see that the slope here is 2, the slope here is 1. Well, if I use adaptive, as it predicted, the work is not significantly more, at least in the rate, and also here in the constant, as you can see, than just using 2 to the power L samples at every level, for every sample deterministically. So the work of the adaptive algorithm is still growing like 2 to the power gamma L. On the other hand, the variance, so the blue one is the adaptive, the variance is converging as fast as if I'm using the maximum number of samples for every sample of X. Okay. So you see that in green, the slope here is half, while in the red and blue, the adaptive and the overly worked estimator are converging at double that rate, the rate 1. And here is a check in the error. We don't have yet complete analysis of the bias of the adaptive algorithm, but numerically, at least for now, we see that it's this is a work in progress. But numerically, we see that it's not. It's following the NL equal for NL, the red curve when NL is equal to 4 power L. So that's the first example. The second example I'll be looking at is digital options. So here we have a geometric Brownian motion, just as a simple example with some parameters. And we want to compute the expected value of an indicator x greater than 0, where x now is, again, this st minus k being some strike. We use, in this case, Euler-Maruyama with the step size 2 to the power minus L to approximate S. And I have the same notation as before, XL, FL, and delta LF. So now when I sample delta LF, I need to sample both XL plus eta L and XL minus 1, eta L minus 1. And I use the same Brownian path in both of them. That's how I ensure that the variance convergence assumption is satisfied. And we use a Brownian bridge when we need to refine. So we have the same Brownian path. We fix that Brownian path, and we use a Brownian bridge when we refine XL and XL minus 1. So they're both being refined independently, but using the same Brownian path. That the fact that they are both being refined independently ensures that we have telescoping sum of the multi-level Monte Carlo construction. And here sigma L is 1, is sufficient. And actually what can show, and I think Mao and Chaim showed that the moment and density assumptions that we listed are satisfied when sigma L is equal to 1. Sigma L, if you can come up with a better sigma L than 1, you can improve maybe the constant, because then you're not overestimating or underestimating the error, sorry. But for in terms of rates, sigma L equal 1 is sufficient. And the curves here are similar to what we showed you before, where the plot of WL versus L, I have the green curve and the blue curve being the one with the minimum effort per sample, and the adaptive one are converging at the same rate or increasing at the same rate, while the variance of the adaptive is decreasing as if I'm using the maximum effort per sample. And here the slope, so here the slope is 1, 2, here the slopes is half and 1. So alpha is equal to beta, beta is equal to gamma, equal to 1. And this is again just as a check that the bias is also decreasing. This behavior probably is just due to numerical errors, just because it's very rare to get a positive sample here, a non-zero sample. Right, so I think this is a good time to conclude. So I don't need to tell this audience that MIMC is a great method, because it allows us not to compound the cost of sampling in the Monte Carlo sampling with the cost of the cost of sampling the X or approximating the samples with the cost of Monte Carlo. It requires, however, some regularity assumptions on the estimators and also the functionals that we're computing. Adaptive sampling, as I presented it here, can relax those assumptions on the functionals. And what it does that by relying on the density of the underlying estimator. So that density is regular, and the regularity is encoded in this analysis by the finiteness of these skew moments. And by relying on that regularity, I can relax the assumptions to get similar, more or less, up to a factor complexity as if I don't have that function. And as you saw, it's fairly general because it does not, the adaptivity actually does not require any further assumptions beyond what is required for the multi-level Monte Carlo assumptions, for the multi-level Monte Carlo analysis in the non-adaptive case. So those two key assumptions that I presented on the density being linear and the Q moments being finite, those were also required for at least the analysis of the multi-level Monte Carlo in the deterministic case. And they're also required for the adaptive case. And finally, just as a next step, and what we're looking forward to now, is that MIMC, multi-index Monte Carlo, as you know, requires much more regularity of the functionals than multi-level Monte Carlo requires. So multi-level Monte Carlo requires only it being Lipschitz to get the same beta. MIMC requires differentiability. And differentiability, actually not just differentiability, but also mixed regularity, so mixed differentiability. My hope is to take this analysis further to MIMC so that I can leverage the regularity of the assumption even further by requiring maybe further moments of the underlying estimator to relax those assumptions on the functional in the MIMC setting. So with that, thank you very much.